Alright, what's up guys? In this video, we're going to pick up with some calculus here, and we're going to be talking about the Taylor series. So we're asked to find the Taylor series for the following function centered at a. So we're simply given f of x is equal to cosine of 2x, and we're given a is equal to pi over 2. So let's just get the distinction between the Taylor series and Maclaurin series out of the way. So remember that a Maclaurin series is just a special case of the Taylor series centered at 0. In this particular case, we're just dealing with the Taylor series. So if I ask you what's the Maclaurin series for e to the x, or I don't know, sine of x or something like that, you already know it's centered at 0. Now, we're not talking about the Maclaurin series in this case, but I did want to just mention that so that we can kind of get the distinction out of the way. A Taylor series can be centered anyway. I mean, it could be pi over 2, pi over 4, wherever they're giving to you, but that's the difference. I just wanted to get that out of the way. And so the Taylor series formula is long, but it's not hard to remember because it's just kind of repeating itself a little bit. So remember, for a Taylor series, we'll have f of a plus f prime of a multiplied by x minus a plus f double prime of a, all divided by 2 factorial multiplied by x minus a squared plus f triple prime of a all over 3 factorial. It'll be x minus a, that's cubed, and you know, we'll just keep going. And that's basically the formula for it. Okay, so basically what we need to do is we're going to go ahead and find f of basically pi over 2. So we just got the function here. So we're just going to take the pi over 2 and substitute it in for x. And then we got to take a couple derivatives, substitute in the value a is equal to pi over 2 for some of the derivatives that we get, and we can construct a Taylor series from there. So it's actually not hard to do at all. So the first thing, let's just compute basically f of pi over 2. Alright, so what's f of pi over 2? So we'll just take our pi over 2 and stick it in. Okay, so we got cosine of 2, we stick in the pi over 2. So hopefully you see that this just reduces down to cosine of pi. Remember, cosine of pi is negative 1. So therefore, we can say that f of pi over 2 is negative 1. Okay, now we just need to take a couple derivatives, and we'll take it from there. Also, make sure that you're good with taking derivatives. It will be very difficult to do the Taylor series if you're not good with taking those derivatives, because you know, we need to get a couple of derivatives. We need to substitute in our value of a. So make sure you're cool with that. What you're given for a Taylor series, you're not going to be given some crazy looking function in most cases, and what we've got here is pretty straightforward, so you won't have anything crazy. But just make sure you're cool with all that taking derivative stuff, otherwise this won't be a very fun exercise. Alright, so f of x is cosine of 2x, and we'll just take a couple derivatives, and typically a teacher or professor will specify you know, how many derivatives they want, or you know, the order, and you know, they'll specify it, but just take a couple derivatives. So let's find the first derivative of this function. So we're looking for f prime of x. Well, that's just taking the derivative of cosine of 2x, which we use the chain rule, and we'll simply get negative 2 sine of 2x, because remember, the chain rule says I take the derivative of the outside function, leaving the inside alone, multiplying by the derivative of the inside, and all I did was move the negative to the front, so that would be f prime of x. And then we'll just take a couple more. So f double prime of x, well, what would that be? Well, that's just the derivative of negative 2 sine of 2x. Well, the negative 2 is a constant, so we can kind of imagine that kind of going away. And we know the derivative of sine of 2x is cosine of 2x times 2. So essentially, if we multiplied, we would just get negative 4 cosine of 2x after we take the derivative here. Let's just do a few more. Like I said, if you're good with the chain rule, you could probably go all day with this. We don't need to really go all day with this because what you're going to see is basically all of our odd order derivatives are going to be 0. And you'll see this once we start substituting in pi over 2. So let's take the third derivative here. So imagine that the -4 is gone. We already know what the antiderivative to cosine of 2x is because we had got it up there. So all we got to do is multiply -4 and -2, and that gives us 8. So this would be 8 sine of 2x. Let's do a couple more. So our fourth derivative here. Okay, well, again, it's just going to be 16 cosine of 2x. All I'm doing here is just using the chain rule. And I guess we could do a few more. Let's say we do all the way up to 6. It shouldn't be that bad. So what's the fifth derivative? Well, in that case, it's just going to be -32 sine of 2x. And we'll do one more because eventually the numbers are going to get a little big. So we ain't going to go too much farther. So let's just do one more. So now when you take the derivative of -32 sine of 2x, in that case that's -64 cosine of 2x. Alright, so I think that's good enough on the derivatives. Now let's just start substituting in what we need. So we already know that f of pi over 2, we already know that's -1. So we're just going to go ahead and deal with our derivatives. So we need f prime, f prime of pi over 2. So we need to substitute that in. So we got our -2, we got sine, and this would be 2. This would be pi over 2. And this is just going to give us 0. Now, when we actually go to construct the Taylor series itself, again, you're going to see how all of our odd order derivatives are basically going to just drop out because they're going to be 0. So we'll just kind of do a few more just to kind of prove it to you. So we got f double prime of pi over 2. Same thing here. We're just substituting it in for x for our second derivative. And if we substitute that in, we'll just simply get 4. I'm going to leave the calculations of how to stick that in, and you do the arithmetic and stuff like that on your own. I'm pretty sure you guys know how to do that. You don't need me for that. Again, we substitute it in. Notice that if we substitute pi over 2 in for our third derivative, keep in mind that we're going to get 0. This is an odd ordered derivative, so we're going to get 0 here. So let's do it one more time. So we'll take our fourth derivative here. Sorry about the noise in the background. That's my nephews fighting over toys. So we're going to stick in pi over 2 for our fourth derivative. So let's stick it in this time. So if we stick it in this time, here we'll essentially get -16 if we stick it in for our fourth derivative. Now, if we stick it in for our fifth derivative, you'll clearly see that we're going to get 0 again. So let's substitute in pi over 2 for our fifth derivative. We substitute that in. You should easily see that we're going to get 0. And then we'll just do one more. And VI. Now we substitute in the pi over 2 again, and we see what we get in that case. And if we substitute it in for our sixth derivative, we'll get positive 64. So this is what we get when we plug in pi over 2. And as you can see, these odd order derivatives are going to drop out. So now all we have to do is get another sheet of paper. That's what we need to do. So we'll get another sheet. And I'm going to go ahead and just construct the Taylor series itself with the zeros in there, just so you can kind of see, just have a general example of what actually happened. but we know they're going to drop out. But I'm just going to show you what actually happens. So we get f of x is equal to cosine of 2x, and when we started plugging stuff in, we see what we get. So we get -1 plus 0 over 1 factorial multiplied by x minus pi over 2, and this would be plus 4 over 2 factorial x minus pi over 2. Don't forget that that's being squared. Then it's going to be plus 0 over 3 factorial. Hopefully you're seeing what's happening. It's going to be x minus pi over 2 cubed. And we would just basically keep it going. So we do got a -16 here, so it's going to be -16 all over 4 factorial. This would be x minus pi over 2 raised to the 4th power. And it would just basically keep going. And I know we took 6 derivatives, but you get the process here. So our odd order derivatives are dropping out. Now we'll need to clean up a little bit of stuff. So remember, 2 factorial is just 2. Whenever I ask you what is 4 factorial, 4 factorial is 24. So how do I know that? Well, a factorial is, or 4 factorial in this case, is just going to be 1 times 2 times 3, and then times 4, basically. And that gives us 24. So let's just clear a couple of things up so that we can get our final answer. So 2 factorial is just 2. So since 2 factorial is just 2, well, if we had 4 divided by 2, we know that that just gives us a 2. Okay. We know that 4 factorial is 24. Okay. And since we know that 4 factorial is 24, we would essentially have -16 over 24. So we could reduce that down to -2 over 3. 6 factorial is 720, I believe. And factorials tend to get a little difficult to do once you start getting past 6. Let me check. I have, I think I got like the first 8 or 9 memorized, but after that I don't have them all memorized. But let me just quickly check to make sure I'm right on that. Oh, and by the way, I wanted to show you guys how to get to the factorials on a calculator. Now, I don't know what kind of calculator you guys have. I have a TI-84 Plus, so maybe you got a different one. And I had some questions in the previous video that I did with Maclaurin series, and they were asking, like, how did you get to the factorial? So I don't know about TI-85 or whatever. I can only go off of mine. So simply what you do here is you type in, whatever you want. So in this case, we want 6. So then I'll just go over here to the math section. And what you do is you go all the way over here to PRB. And if you go down, you see the exclamation point. And you'll click on it. And yeah, that's right, 720. And that's essentially how you get there. So in that case, if we were to go ahead to our 5th derivative, not our 5th derivative, but our 6th derivative, because we know the odd order derivative would drop out. For our 6th derivative, in that case, it would just be 64 over 720, and we would reduce that in a calculator, which is quite easy to do. So we can actually, if we want to, go ahead and write out with all our derivatives, because we have the assistance of the calculator, and we'll let the calculator do all the simplification as it pertains to the fractions for us. So let's write down our Taylor series expansion for this function centered at pi over 2. Cosine 2x, again, a is equal to pi over 2. Alright, so Taylor series here, just going to be -1 plus 2 multiplied by x minus pi over 2, quantity squared, minus 2 over 3, x minus pi over 2 raised to the 4th power. We keep reducing here. this is going to be plus 4 over, I believe this is going to be 45, but I'm going to check anyway. And it's going to be x minus pi over 2, all raised to the 6th power. And, you know, just keep going. And let me just quickly check. I kind of did that in my head, so let me make sure that's right. So you got 64 over 720. Yeah, 4 over 45. And basically the way I did it was, I'm really good with calculating. I try to find common factors of the two numbers and see, based off of the common factors I can find the two numbers, I can easily reduce most of them in my head, or most fractions, even if they're big sometimes, because I'm good with kind of finding common factors and seeing how we can actually reduce it down. And it will keep going. So basically that's going to be your Taylor series expansion for this function f of x equal to cosine of 2x at a is equal to pi over 2. Okay, so maybe a little bit more of a lengthy explanation than I intended for, but hopefully you were able to see the whole deal with the Taylor series. All right, so let me know if you guys got any questions. I will see y'all next time.